Tangents and Velocities, Part 2. In the last video, we introduced the idea of using successive secant lines to approximate the slope of a tangent line. Since we're going to be finding the equations of lines in calculus, let's do a quick review of how to find the equation of a line. In this case, we want to find a line that satisfies these conditions. We want it to be through the point 2, 7 and parallel to the line passing through the points 3, 5 and negative 1, 1. Lines that are parallel have the same slope. So before we can write the equation of this line, we need to find the slope of the line. Since it's parallel to the line through these 2 points, that means that we can find the slope of our line by finding the slope between these 2 points. So that slope will be equal to the difference between our y values, so that'll be 5 minus 1, divided by the difference between our x values. And we want to make sure that these are corresponding x values. So since we used this 5 as our y2, this 3 will be our x2. So we have 3 minus, and since we used this one as our y1, this negative 1 will be our x1. So we have 3 minus negative 1. So our slope is equal to 4 over 4, which simplifies to 1. And I'm just going to circle that 1 so that I can find it a little easier later. So now we know the slope of our line, and we also know one point on our line. Since we know the point and we know the slope, we probably want to use point-slope form. So point-slope form is y minus y1 is equal to m times the quantity x minus x1, where the regular old y without subscripts and regular old x without subscripts are variables, and we're going through the point x1, y1. So we have y minus y1, which is the y value of our point, so that's 7, is equal to our slope, which we found was 1, times the quantity x minus the value of x1, which is 2. And then we just want to simplify this a bit. Sometimes you can leave it in point-slope form, but it's good practice to put it in slope-intercept form just in case. So this would be y minus 7 is equal to, well, 1 times the quantity x minus 2 is just that x minus 2. And then we want y equals, so we need to eliminate this minus 7. So we'd add 7 to both sides, and we'd be left with y is equal to x plus 5. And this is the equation of a line that goes through the point 2, 7 and is parallel to the line passing through the points 3, 5 and negative 1, 1. A lot of these problems are application problems, so we need to be used to a lot of the notation that we use in physics, where S of t will give us the position, v of t gives us the velocity, a of t gives us the acceleration, and j of t gives us something called the jerk, which you don't see too frequently in calculus, but it's kind of funny. Now we can start getting into some calculus. So the goal of this problem is going to be to approximate the slope of the tangent line, so that instantaneous velocity, by finding subsequent secant lines, which give us that average rate of change. So let's take a look at this. If a rock is thrown upward on the planet Mars with a velocity of 15 meters per second, its height in meters t seconds later is given by the equation y is equal to 15t minus 1.86 t squared. So this equation, y is equal to 15t minus 1.86 t squared, is our position function, s of t. And we'll start by finding the average rate of change. So that's our slope of the secant line. And this will be over various time intervals. And this is where notation can get a little weird. So for these time intervals, we're going to be using these brackets. So the interval will be t naught, comma t1. And you'll notice that both of these values here, this t naught and this t1, are both inputs. They're both times. So this is not an ordered pair. It's not an x comma y, it's more of an x comma x. So we're just talking about over what interval of time are we interested in this function. And the average velocity, that v sub average, is given by this s of t1 minus s of t naught all over t1 minus t naught. And this is just the same as saying we're finding that slope of the secant line. So if we look at this left side of our table here, we're given various time intervals, that t naught, comma t1, and these are just our time intervals. And we want to calculate the average velocity between each of these time intervals. So, for example, if we're trying to find the average rate of time for this first time interval, that means that we need to find the value of s of t1, so that'll be s of 2, minus s of t naught, so that'll be s of 1, all over 2 minus 1. And when we substitute this into our function, we'll get something that's rather a mess. So this will be s of 2, so that's 15 times 2, minus 1.86 times 2 squared. So that's our s of 2, minus s of 1, substituting back into that position function. So that's 15 times 1, which is just 15, minus 1.86 times 1 squared. Well, 1 squared is 1, so 1.86 times 1 squared is 1.86. And this is all over 2 minus 1. And this is quite a problem if we were trying to do it on paper without a calculator. So luckily, if you had this problem and had to fill out this table on your own, you'd have access to some sort of calculator. But this would be equal to 9.42 meters per second. And that's the average velocity over that interval from 1 second to 2 seconds. After completing the calculations, you should find this table. So if you were doing homework or some sort of practice problem where you'd have access to a calculator, you might actually have to calculate these. But if it were something like a quiz or test in a class where you didn't have access to a calculator, you'd usually be given this table already. And then you'd use this table in order to estimate an instantaneous velocity. In this case, we're looking at the instantaneous velocity when t is equal to 1. When t is equal to 1, that means that we're looking at the time interval from 1 second to 1 second. Just in that moment, what is the velocity? If you look at the time intervals here, they're arranged in such an order that as we go down our table, we're getting closer and closer and closer to that time interval 1, 1. this T0, this first time is staying 1, and then this T1 is getting closer and closer and closer and closer and closer and closer to 1. And what we're interested in is, as we're getting closer and closer to that point t equals 1, what's happening to the average velocity? Now, this is a numerical approach. We're just crunching numbers, looking for patterns. What do we see? So when we do something like this, there's a bit of approximating that has to happen. So if we look at this, we see that as we get closer and closer, the difference between these average velocities is getting smaller and smaller and smaller. So let's see, it would probably have this 11 here. And then, let's see, the difference between 11.26 and 11.28 will be 2/100ths. So the next difference will probably be even smaller than that. So this is probably something around 11.29 meters per second. And that's just the estimate. It's just a guess. We're not quite sure, but it's probably close to this value. Okay, let's look at a slightly more complicated problem. For this one, we have the point P, which is 7, -2, lies on the curve y is equal to 2 over the quantity 6 minus x. This image here is the graph of y is equal to 2 over the quantity 6 minus x. And then we have this point P here, which is that point 7, -2. In addition to this point P, we have a point Q. Point Q is the point x, 2 over 6 minus x. So point Q is a point that is changing. That means that it could be this point, this point, this point. It could even be one of these points. But because the point of this section is to take our secant lines and use them in order to approximate a tangent line, that means that we're probably looking at this point Q. These are all many different point Qs that should probably have subscripts. And we're looking as they get closer and closer to this point P. Now let's actually take a look at different points Q. So again, Q is the point x, 2 over the quantity 6 minus x. And we're looking at what happens to the slope between P and Q. So that's this MPQ, the slope between P and Q, as the value of x changes for Q. So if we look at our table here, as we go down from here to here, at these different 6 and 9 somethings, we get closer and closer to 7, starting at x values that are to the left of 7. And then if we look starting at the 7.1, we get closer and closer to x values that are 7, starting from values that are to the right of 7. So we're getting closer and closer to this point 7, -2. Now let's find the slope of PQ. So that's the slope of the secant line between P and Q. The first thing we'll need to do is actually find this point Q. So let's just start by finding MPQ for this 6 and 9/10. And before we can even find that, we actually just have to find the output of our function there. So at x is equal to 6 and 9/10, we have to find our y. So y will be equal to 2 over the quantity 6 minus 6 and 9/10, which will be equal to 2 over negative 9/10, which is a bit tricky to deal with here. But the way I like to think of this is as a 2 over, and then I'll rewrite that negative 9/10 in its fractional form, so that'll be a negative 9/10, which gives us negative 20 over 9. So that means that Q at this particular x value will be 6.9, comma, negative 20 over 9. And I know that I'm mixing fractions and decimals here, but if we were to rewrite this negative 20 over 9 as a decimal, it would be negative 2 and 2 repeating. And repeating decimals are kind of difficult to do quick math on, so we'll leave that as a fraction for now. So now that we have point Q and point P, we can actually find the slope between these 2 points. So that MPQ. And that will be equal to the difference between our y values, so negative 2 minus negative 20 over 9, all over 7 minus 6.9, or 6 9/10. So this will be equal to, well, let's rewrite that negative 2 so that we have a common denominator. So that'll be negative 18/9. And then if we're subtracting a negative, that's the same as adding a positive, so adding 20/9, all over 7 minus 6 9/10 gives us that 0.1. So this is equal to, well, negative 18/9 plus 20/9 gives us 2 over 9. And then we can rewrite that 0.1, or 1/10, in its fractional form, which is, of course, 1/10. And then simplifying this, so that's 2/9 times 10 over 1, which is equal to 20/9, or 2 and 2/10 repeating. And we need how many decimal places? 6 decimal places. I need more room for my decimal places. So that would be 2.2222222. 6 2's. And this is definitely a problem where you want to use your calculator. But this is where these numbers would come from. So after completing all of your calculations with a calculator, or if it's for your homework, I would probably use an Excel spreadsheet. You should get these values. So now we can use this table of values where we have the x values of Q and then the slope of the secant line between P and Q in order to approximate the tangent line at the point P, which is this 7, negative 2. So we want to look at what's happening as our x values get closer and closer to this 7. What is happening to the slopes of our secant lines? Are they also getting closer and closer to something? If so, they're probably getting closer and closer to the slope of the tangent line. So if we look from the left of that 7, so starting with numbers that are smaller than 7, so that's here from the left, we see that we kind of get closer and closer and closer to perhaps 2. And then I'll recolor this with a slightly lighter green. So if we look from the right, so starting with numbers that are bigger than 7 and getting closer and closer to 7, the slope between P and Q, so the slope of the secant line, seems to also, why are you yellow now, or orange, be getting closer and closer to 2. And since we seem to be getting closer and closer to this 2, the slope of our tangent line is probably about 2. We can then use this slope in order to find an equation of the tangent line at that point. So since we have a slope and we have a point, we use point slope form. So that y minus y1 is equal to m times the quantity x minus x1. So that'll be y minus negative 2 is equal to the slope of our tangent line, or in this case, the approximate slope of our tangent line. We can't be sure, but numerically it seems like it's probably 2. So that's 2 times the quantity x minus x1, which is 7. And then sometimes you can leave this in point slope form, but it's really good practice to get this in slope-intercept form. So let's simplify. So this will be y plus 2 is equal to, and then we'll distribute that 2. So 2x minus 14. Then we'll solve for y. So we'll subtract 2 from each side. And we're left with y is equal to 2x minus 16. And that is the approximate equation of the tangent line at the point P, which is 7, negative 2. In the next series of videos, we're going to take a closer look at this idea of approaching with something called the limit of a function. Approaching is really, really important in calculus. So limits are also really, really important. We're going to take a step back from examining the slope, which is what we've been doing, looking at slopes of tangent lines and secant lines. And instead we're going to actually look at the output of a function, so the value of f of x or y.